Madeline, can you hear us?
Yes.
We can't hear you.
You cannot hear me. Oh, okay. Sorry, can you hear me now in the room?
Yes, we can.
Yes.
Okay. Sorry. Do you want me to just go ahead and get started?
Yeah, you could put it into full screen mode if you would.
Yes.
And then go right ahead.
Great. Okay. Hi. I'm Maddie. I am a PhD candidate at the University of Oklahoma. I work under Dr. Stephen Cavallo. What I study is this short-term and subseasonal Arctic sea ice loss. Actually what I do isn't, sorry, Kathy was helping me out getting some data, and she was intrigued by some of my results and suggested I present it here. So this is probably going to be a little different from what y'all are used to seeing. So what I am interested in, like the main topic of like my whole dissertation, has to do with these sea ice loss events called very rapid sea ice loss events, which is when you lose a lot of sea ice in a short amount of time, something like, almost 250,000 square kilometers in a day of sea ice loss. And a great example is kind of pictured in that mustard yellow color on the screen, which is the amount of sea ice loss that's associated with the Great Arctic Cyclone of 2012. If you're not familiar with that, if you don't think about Arctic stuff all the time, 2012 still holds the record for the least minimum sea ice measured. And 4.4% of that total sea ice loss for that season was from this one cyclone. So this one event accounted for 4.4% of the total sea ice loss for that whole summer and contributed to that still held record low. So overall, for my dissertation, what I'm really interested in is like what causes these types of events. And that is a remarkably difficult question to kind of get your hands on. And so one of the things that I did was I just wanted to see how well CESM2 in the large ensemble performs at capturing these types of events specifically and kind of subseasonal sea ice loss generally. And some of that was like evaluating, could I use CESM2 as like a tool to approach this problem from a modeling perspective? Spoilers, the answer to that was no. And so we'll get into that. So long story short is that CESM2, both in the large ensemble and in like the S2S reforecasts, doesn't capture these type of events well. So let's start from like the big picture and then zoom in. This is why that type of sea ice loss events is kind of important for several reasons, but let's jump into the CESM2 stuff. So one, as everybody here probably knows, CESM2 has a strong negative bias in sea ice extent for all seasons. That is kind of a well-known problem. It's thought that's related to not getting enough refreezing in the winter. And when you use, instead of CAM6, when you use the WACCM6, this gets a lot better. But anyway, so that's kind of an overall known issue. I would like to point out here that while we get a pretty close approximation of the September climatological trend in sea ice extent, in CESM2, we don't get that for the March. So the March trend is kind of missing in the large ensemble. if instead of looking at, this is the seasonal, so the annual minimum in September and maximum in March in our CS extent, if instead of just looking at that, we look at the whole annual kind of plot. So this is CES extent over time. Blue is CESM2 large ensemble. The solid line is the average, and the shading represents the interquartile range. And then the red is that same for NSIDC, the National Snow and Ice Data Center. And then the dashed line represents the record minimum in both data sets. And so something that I found pretty interesting in this is that just kind of pointing to these shorter timescale processes that those might be missing in CESM2 is how thin that interquartile range is in CESM2 versus NSIDC. And so we're seeing less year-to-year variability in our CASE extent in the like model world versus observations. And so that's just kind of a little nugget we're going to put in the back of our mind and keep looking at these comparisons on a large scale. So the next thing I did was do a power spectrum on both data sets. So the black NSIDCs on the left, CESM2 large ensemble on the right. The black is the power spectrum. The red line, which is kind of hard to see, is going to be that red noise spectrum, and the green is the 95% confidence. So when we're looking out to like annual timescales and like annual and seasonal, we're hitting those same power peaks in the model as compared to observations, kind of one after another right there. That's looking really good at these large timescales. But when we zoom in to our smaller timescales, we see that there's a lot of significant power in NSIDC that is just not present in CESM2. So if we look, say, like sub 20 days or even 30 days, we're getting some power, some significant power at that like 30-day mark over in the CESM2 large ensemble, but not nearly as much as we get in NSIDC. So again, pointing towards not capturing some of these short-term sea ice processes. Okay, so I go from looking at the power spectrum to then identifying these very rapid sea ice loss events, or VRILs. And the way we do that is so we take our daily change in sea ice extent, and we're going to filter, we're going to do a 5-day running mean and filter out everything with a period greater than 18 days, and then take the bottom 5% of loss events. So the 5% most extreme loss events when we're excluding seasonal cycle and we're excluding climate change. I don't know if I said this, but I do remove the linear trend in that as well. So when we just look for those events, this is just kind of the number and size of each event as a function of year. In CESM2, I'm looking at a single member out of the large ensemble, and I'm looking at the member that most closely represents the ensemble average, and then I'm using ERA 5. So the big pinks that you're seeing there are the size and then number. They're stacked on top of each other if they happen in the same year of these VRILs in NSIDC. And then these little dark purples down here are the same thing, but in CESM2. And so what I want you all to take away from this slide is that when we find the exact same type of ice loss event, kind of when I force the data to spit out these extreme events in the large ensemble, the amount of sea ice loss is like an order of magnitude too small in CESM2 large ensemble. And so, yeah, so just feeding into this, we're missing these short timescale processes. In addition, we're going to find that the atmosphere associated with these ice loss events is really, really different in ERA 5 versus CESM2 large ensemble. So what you're looking at here are composite means of the contours are mean sea level pressure. In ERA 5, I have the color fill is, I'm looking for tropopause polar vortices. So this is potential temperature on the dynamic tropopause, but I don't have that same data for CESM2, so you can kind of ignore the color fill. So the moral of the story is, in ERA 5, if I take a composite of what the atmosphere looks like right over this type of ice loss event, I get a strong pressure gradient at the surface that's not present in CESM2. And if I recenter that pressure gradient, recenter my composite, excuse me, so that I'm over centered on the closest local minimum, I see a surface cyclone and a strong surface cyclone signal. And we do see that in CESM2. So what that is kind of hinting at here is that even though we're not losing as much sea ice as we should for these types of ice loss events, in both ERA 5, kind of both in observations and in CESM2 large ensemble, we do get an association of this type of sea ice loss event with a surface cyclone. So that is good. We're at least capturing the cyclone, even if we're missing that pressure gradient. This is that same composite, but for winter, and it just tells us the same basic story. Okay, so now let's jump out of large ensemble and go to these, the S2S reforecasts. And so I used the reforecast data because I wanted to look at some, compare specific virials between how they're represented in CESM2 and then in observations. And I have 4 examples, but I want to give ample time for questions. So I think let's just go over one of them in detail because the overall story is the same between all 4 of my examples. And so I want to go ahead and go to the Great Arctic Cyclone because that was one of my cases. Yeah, so before we look at some stuff for that one in particular, these are the daily change in sea ice extent for all 4 cases. The sea ice loss associated with the Great Arctic Cyclone is down here in panel C. And this is all 11 of the members. When we look at virials in space, I'm usually looking at the 5-day change in sea ice concentration. And so that's kind of what we used. That's what I used to pick my which run of the reforecasts to use. I wanted to get as close to the virial as possible while still allowing for that like 5-day change. And so for this August 9th virial, so notice the August 9th virial, so the actual amount of sea ice loss on that day is like negative 0.18 million square kilometers. And at best, even if we back that up a couple days, at best I'm getting 0.08 sea ice loss in that same kind of time frame. And so not quite off by an order of magnitude, but off by more than a factor, like we're like a factor of 2 off. And so still much too small, not nearly enough sea ice loss for any of these virials in any of the cases. Okay, so that's not the one we're going to look at. Let's look at this guy. So at first I used the reforecast that was initiated on the 30th of July. And unfortunately, because my choices are 30th of July or August 6th. And so August 6th doesn't give you enough time to like see that sea ice loss. But unfortunately, the 30th of July reforecast really struggled with the atmosphere. So I want to talk about this for a little bit. On the left, those left columns, that is the 5-day change in sea ice concentration. On the top is NSIDC sea ice, and then the bottom is CESM2. The reforecast. And then on the right is the 5-day mean in mean sea level pressure and 2-meter winds. And then the location of the virial is circled in all 4 panels. So the first thing I want to point out is that when the reforecast was initiated on the 30th of July, it completely misses the Great Arctic Cyclone. So instead of this very strong, it's in the top 5 of deepest cyclones, deepest summer cyclones of all time in the Arctic. Instead of that, we get a weak high pressure system. And so, so that was concerning to me. And May is going to make a challenge to kind of analyze this. And then the other thing that we're going to see is while we're not really losing a lot of sea ice in the right spot, there is really widespread sea ice loss and that is probably what we're seeing here of this blue is a really aggressive seasonal cycle. So 2012 was going to be a very low sea ice year even before the Great Arctic Cyclone. But the Great Arctic Cyclone kind of kicked it into overdrive to get us that record minimum. And we're seeing this sea ice loss here. What looks wrong to me as someone who spends way too much of their time looking at changes in sea ice extent is this blob here of loss. This is over the central Arctic. This is multi-year sea ice instead of like first year ice. So this is not where we expect loss as part of the seasonal cycle. Along the edges over here, sure. But even notice that in reality, we have slight growth in these regions where we have loss in the model. And so this sea ice loss here in the CESM2, even in the S2S as opposed to the large ensemble, it's too deep into the central ice pack. That's not where we should be losing sea ice concentration. This isn't loss of thickness. This is saying that this is in that grid cell, there are pieces of open ocean, right? That whole grid cell is no longer covered in sea ice if we're having negative change over here, which doesn't make a lot of physical sense to me. Okay. And so because we fully missed the Great Arctic Cyclone, I went ahead and looked at the reforecast initiated on the 6th of August, and there's the Great Arctic Cyclone. It's not quite as strong. It's not quite as deep in terms of that minimum mean sea level pressure, and it's a little shifted towards the central Arctic. So that's important here because we want this to get this ice loss event. We really want to see that cyclone interacting predominantly on the sea ice edge. But we're getting the associated cyclone here, which is great. And we actually end up with less overall sea ice loss here, but it is closer to the correct location, and we're having less of that kind of aggressive seasonal loss where in NSIDC we're seeing growth. And so my takeaway from this is that CESM is actually pretty good at when we're close enough to the start of the reforecast, right? We're doing a pretty good job of finding the cyclones, right? The cyclones that are almost always associated with these types of loss events, but are consistently getting not nearly enough sea ice loss associated with it. So that to me, that's pointing at a missing process. So there are 3 main thoughts on what causes this type of sea ice loss event. One is going to be heat transport from lower latitudes. So specifically thinking about bringing up like warmer, moister air, or getting that like warmer, moister air from like the cyclone to drive melt. The second is going to be ocean waves directly interacting with the sea ice itself and like breaking it up, making it easier to both transport and melt. And the third is going to be vertical mixing of the ocean. So forgive me if you know this, but the Arctic Ocean has a it's cold enough that its density is predominantly a function of salinity, not temperature. And so you have a cold, relatively fresh water cap at the top, and then below that is warmer but saltier water. And so when we have these like strong winds associated with this cyclone, you can have that vertical mixing to bring up warmer water from below and then melt. And so it's really these two ocean processes that are the big open questions of what's driving these sea ice loss events. Currently, at least in the large ensemble, CESM2 does not allow ocean waves to interact with sea ice. We don't really know how that works, right? How those ocean waves would break up the ice. In fact, currently there does not exist anywhere on God's green earth any type of model that allows ocean waves to interact with sea ice, even like just a coupled sea ice ocean model. Allows it to interact dynamically. And so it is my hypothesis that those ocean waves actually are playing more of an important role, though the vertical mixing of that, those like the thermal component of the ocean and that vertical mixing. I recently saw a presentation that was showing CESM2, but this is all models struggling to allow that vertical mixing under sea ice. So I am sorry if that was a little rambly. I am currently 29 days, T-minus 29 days to my dissertation being due, so I'm a little frazzled, and the toddler was sick all weekend. But I would be happy to take whatever questions you all have.
Thanks, Nadia.
We have time for a question or two. Nothing online. I'll ask a question. Maddie, you started off showing the bias in CESM2, and then you switched to CESM2 S2S. You show the bias there. I mean, could this, anemic sea ice response to this cyclone be associated with climatological bias in the S2S?
Yeah. So I think climatological bias in the S2S. So what's tricky with that is that the overall bias in the large ensemble is we lose too much sea ice and then we don't grow it back enough. And so I had actually initially thought that in the S2S, we might see really aggressive sea ice loss, right? Because that would be, in my brain, more consistent with the overall biases. But since we're seeing this kind of anemic response in these short timescale processes, I think it's more pointing at like the missing physics than a climatological response. Something that is really cool is when you have these types of events in winter, the net response over like a couple weeks can actually be increased growth because the initial loss opens up more ocean to freeze. And so by not having these short timescale processes, that could actually be accounting for some of the like difficulty in refreezing enough in the winter. Does that answer your question?
Yeah, that's great. Thanks a lot. All right, we should move to our next speaker, Sanjeev Kumar, another online speaker. Sanjeev, are you there?
Yes, I'm here. Let me figure it out how to share my screen. Window. Okay. So can you see my screen?
Yes, and we can see the.
Okay, so is it full screen mode or the presentation mode? Yeah.
think you need to go to full screen mode.
Okay.
Right now, we just see all the slides.
Can you see it now?
No, we're not seeing full screen mode.
Mhm. Window. Does it work?
Not yet.
Okay, I think this is good enough. Okay, hello everyone. I'm Sanjeev Kumar from Auburn, and as you are seeing in this picture, I'm going to talk something about Hoover Dam. And from that, what we can learn about using the water data, what we can learn about the climate system. Here is a little update on the Lake Mead water level. I update this figure almost last 2 to 3 years every year. And over the last 1 year, like this is annual average of the Lake Mead water level. In 2023, there was a uptick of around 8 feet. However, if you see like how much water declined from 1998 to
Sam,
2020.
sorry to interrupt you, but we're not seeing your slide advance.
Oh,
Thank you. That's good.
okay.
That's good now.
That is good enough?
Yeah.
Okay.
You can see
So I think I'll keep this mode if that works. Okay. Yeah, if you see like between 1998 and 2022, we have a decline of about like 163 feet. And if you were to visualize like 28 of us can fit into there. But a second thing that's important in this graph is all these 163 feet decline has occurred in a cluster of time, like from between 1998 and 2022. So such clustering of wet or dry event is called what is called like persistence or the there are different names I'll come across. Okay, or the low frequency climate variability, that is one of the title. Okay, so how do we measure it in a climate system? If your previous speaker has already introduced you that frequency analysis, if you plot the same time series in the kind of frequency domain, what you see, I'll contrast it, like compare and contrast. It's one of the things. So if you wear the white noise, you will just see the flat line, like all the frequency has a similar power. Whereas if it were to the red noise, then some of the lower frequency will have the higher power as depicted in the red line here. And you can write the equation. Both the equation are little different from white noise versus red noise. So think one more piece in the background is we'll use the central limit theorem. So here is a synthetic data that I purposefully designed as a kind of nonlinear data set. I put some noise, almost half of the standard deviation of the X. And you see there is a nonlinear part in that system. However, if I take the same data point and average it across like in this case, like a 30-day running mean, I applied it. And you see, the system goes into somewhat what we can characterize as sort of the linear system. So we'll use this property to understand something useful out of this water data. Okay, those two are good enough, the background information. Then I took the soil moisture data set that is shown on the kind of one of the lower panel. And if we run through a similar sort of frequency analysis, what you are seeing in the top plot is the black line is the observation, means the ERA5 land soil moisture data set. As well as there are two other large ensemble data sets. Both are shown in the color. Those two are two different large ensemble data sets. So as you go towards the lower frequency, like 1 or 2, you see that the power in the climate model is somewhat lower than the black line. That's what we say that this low frequency is sort of underestimated in climate model. And you see that the red process means the yeah, we have the, at least in the observation, there is a higher power in the lower frequency than the other frequency. And that's one evidence. You can look into the different metric, like the previous was the soil moisture. This is the precipitation. Again, observation time series is shown in the bottom panel. And there are even different nomenclature, like either the Hertz exponent, Hertz coefficient, or long-term persistence. I think we are through these different nomenclature in the literature, we are trying to refer to the same processes, like what's a low frequency variability in the climate system. And here almost there are 228 ensemble from CMAP6 in the top panel. There is observation in that kind of a black dot, and then you have the CSM2 large ensemble. You see, yeah, there are few ensemble that correctly picks up that observation, but like almost I computed it almost 90% of both the CMAP6 as well as CSM2 large ensemble shows underestimation of that persistence even in the precipitation data set. Okay, I'll give you one more piece of evidence. Yeah, if you go and look into the literature, like what are the different low frequency variability in the climate system and its representation in the climate model, there are enough literature to suggest that these frequency has been underestimated by the climate model. There are more literature in the hydrology as well as the climate science. Okay, we'll take a break and think about like why is that, and I'll try to give you a answer. You may have a different answer, but I think I was happy with the answer. Like I got something sensible out of a small exercise. Let me see. So I worked with Matt Newman in kind of my previous position, and one thing we learned about this redundant ENSO model. So in the redundant ENSO model, that is model 1, we are trying to predict the next year's soil moisture, that is ST, as a function of the previous year's soil moisture, that is ST minus 1 in the model 1. And then we will assume that since I'm not an ocean person, we'll assume that we know the ENSO prediction for that year. So that is ET. So we know the concurrent ENSO for a given year, or we'll make a bold assumption that ENSO is correctly predicted. And then we will add the soil moisture from the previous year, and then we'll try to develop this simple linear regression model. Again, I'm using the 12-month running mean, so that way this linear assumption would valid here. Then we'll have some noise term to represent that variability part or internal variability part. And if you develop this model, model correctly captures or almost correctly captures both the observation as well as in here I show you one of the large ensemble data set. And in the next slide, I'll show you model scale. But here in terms of the frequency diagram, it captured those sort of variability. It has its redness and it has using the observation, you can make this model. Using the large ensemble data set, you can make this model. So now we have this model, and in the next slide, you'll see its scale. But what I can additionally do in this model, once the model is satisfactorily developed, you can remove that Sol moisture component like T minus 12. And then again try to build this model in this regression based modeling. And what you find, if we remove that T minus 12, that is the memory part, you do not get that redness or that low frequency variability in the power spectra. You still get that ENSO part in the model too. So we'll show you one slide. How does this simple regression model does? In the left hand side, it is a redundant model for 1 year lead. Next year's almost prediction using the observation, and its comparison what comes out of the Smiley data set. And it looks very much comparable, even when it is slightly better, but probably it is because like in the Smiley data set, only 10 centimeter soil moisture was there. So given this model at the internal time scale is doing okay. So you can ask a different question here, like can the ENSO only model give you the can usefully predict the hydroclimate? Some of the discussion was there today morning, and so if this is the left hand side is your redundant, so we keep that memory component coming out of the previous year. In the right hand side, I remove that. This is model 2, we only keep the ENSO. And if you consider like only 0.5 and greater to be useful skill in the case of the ENSO, you get some skill, but it is a kind of 0.26. So by that 0.5 criteria, you would not call as a kind of a useful skill if I were to know only the ENSO and then I were to predict the soil moisture. Okay, so here it's sort of answering the question, why do the climate model predict low frequency, under predict the low frequency hydroclimate? So since I have this regression model, I can make that regression model using the observation data set. That is your kind of first group of the 2 bars. Then I can make the same model using 2 of the large ensemble data sets. Those are the next 2 group of the plot. And what I want you to compare this blue versus the red, what is the ratio of the prediction skill coming from ENSO versus the memory component. And if you see the observation, that is, if you pay attention to the secondary axis of the y-axis, secondary y-axis, you would see that in the observation skill are 50-50 split, like 50% of the skill is coming from the ENSO and 50% is coming from the memory part. Whereas in both the climate model, most of the skill is coming from the ENSO. Almost 90% of the skill in the climate model is coming from the ENSO. So my interpretation of this result using this simple regression analysis is there is too much ENSO in the climate model prediction, and that's what it leads to underestimation of the low frequency climate variability in the climate model prediction. Let me see. So what my hypothesis is, there is atmospheric input part that is relatively whiter. Those whiter input is get redundant by the memory process over the land. There can be a number of example there, either that it's memory, it's reemergence, or the vegetation extracting the water from the previous season. So those processes brings the redness in the spectra. And if you remove those redness from the model, you would if I remove in the model 2, I remove that interaction component, and then the redness is not there. I think there are implications across scale. There I showed you interannual time scale. This is just 1 month to the next month. One is a control run that you can think about sort of the observation. Another is randomized run, so that we know the difference between what is what we should expect and what it look kind of in the case of randomized atmospheric forcing. And in the bottom panel, you see all the CSM2 large ensemble, the same analysis, and you would see that, yeah, it looks more, at least in this example, more like a kind of randomized forcing than what you would expect in the control or the observation case. So I think I'll stop it here. This is the same slide as I presented it earlier. Thank you.
Any questions? I have one question, Sanjeev. So one potential source of this low frequency variability is coming from the Atlantic scale variability. So, I mean, have you thought of trying to relate this deficient variance to deficient AMV, in particular the subtropical lobe of AMV in the models?
Short answer is no. I have not yet attempted it. I'm trying to expand on this. This is simple regression model work, like in a follow-up work. I can use some more complex experiment or the climate modeling experiment to kind of differentiate between those individual sources.
Okay, thanks very much. We'll move on. Our next speaker is in person.
Yeah, Torrid. Hi everyone, my name is Kia. I'm a research scientist at NOAA PSL. Today I would like to share my research on making interpretable ENSO forecasting by combining old and new ways of predicting ENSO. This work has been conducted in collaboration with my colleagues in NOAA PSL and CERES. So let's start with deep learning. We all know that deep learning is now everywhere. All field is not an exception. So many previous studies have applied various neural networks to predict ENSO. And these data-driven approaches have shown promising skills, shown promising results. However, it is still
I
hard.
don't think they're seeing it online.
They're not?
I don't think the screen was shared.
speak just a little bit louder.
Okay.
Thank you.
Yeah, so I'm gonna talk about making interpretable answer forecasting using hybrid deep learning and analog approach. So many studies have applied various neural networks to predict answer, and this data-driven approach have shown some promising results. However, it is still challenging to explain their decision-making processes because there are so many numbers of hidden parameters. There are methods called XAI, which try to explain what these black boxes do, but there are also limitations with this method. XAI is a post hoc explanation of a black box, and different XAI methods can give different explanations because there's no grand truth for the attribution. So this figure shows the different explanation for classifying atmospheric rivers, and you can see that different explanation, different XAI can give different explanations, which make it hard to interpret what they are explaining. So to solve this issue, we will use a simple forecasting method called analog forecasting. This is a very simple forecasting method, and I think what everyone does in their daily life. So let's say if today's condition is similar to what happened 2 weeks ago, then you will think similar things will happen again. And model analog extends this idea, and it tries to find states from model simulation that have been run for thousands of years. Because there are so many sample size, it actually provides a very good skill, especially on seasonal time scales. So this figure compares the SSD forecast skill using model analog and North American multimodal ensembles. And especially over the equatorial Pacific, we can see that model analog provides comparable skill to that of dynamical models. However, there are some issues in analog forecasting. So suppose that we want to forecast from this initial condition that's going to develop to a La Nina state in 12 months. To do this, we select analogs from a repository of climate simulations. So these 4 analogs are the closest match to our.
You need to
Yeah.
mute.
Everyone needs to mute, please, except the speaker.
So these 4 analogs are the closest match to our initial conditions based on root mean square distance over the entire tropics. When forecasting, we simply look at their states 12 months later, and we can see that some analogs do a very good job, but some analogs diverge significantly from the desired state. So we can even see, so for analog 4, even forecast the opposite phase of answer, and we can see that the small error in the initial condition can grow significantly, which is also known as chaos or butterfly effect. So the question is, instead of focusing on the entire tropical regions, can we identify sensitive regions? So for this purpose, we use deep learning to estimate weights given an input conditions. This weight shows the sensitive regions where initial error growth is significant, and we aim to find analogs that closely match over these regions. On the other hand, other regions are considered relatively insensitive, so we can allow analogs to differ over those regions. These weights are used for analog forecasting, and we train the deep learning model to improve the forecast skill. Compared to machine learning only method that directly produce forecast, this method is much more interpretable and explainable. The estimated weight shows important regions objectively evaluated by forecast skill. This is a clear benefit over existing many XAI methods, which are post hoc explanation of black box, and each method gives different results. And since this is an analog forecasting method, it can trace the entire evolution of the system based on physical models. We test this idea with CESM2 large ensemble dataset during the historical run. We use the monthly sea surface temperature, sea surface height, and zonal wind stress over 50 degrees south to 50 degrees north. and we split the data to 3 chunks: training, validation, and test dataset. The training dataset is also used as a library to select analogs. So analogs are always drawn from the training dataset, regardless of the period we make forecast. We use the UNet as a deep learning method. UNet has a downsampling encoder and upsampling decoder, where in the downsampling branch, the spatial information is condensed, while in the upsampling branch, the spatial resolution is increased and the feature information is reduced. There are also skip connection, where the high resolution information from the downsampling branch is reused in the upsampling branch. We use SST and SSH and wind stress as an input. And we target SST pattern over the equatorial Pacific on seasonal to annual time scale. Notice that we don't target linear indices, which are average SST over certain regions, but we target SST pattern because individual answer events have significant diversity. Here are the results in test dataset, which is a dataset the model has never seen before. This figure shows the root mean square error of SST over equatorial Pacific. So we can see root mean square error is reduced by 10% at 9 to 12 months lead time. However, we can also see slight increase in errors at shorter leads. This indicates that deep learning assigns more weights outside the equatorial Pacific, which means that other regions are considered more sensitive in this time scale. Okay, so I'm sure that deep learning can improve the model analog, but you might wonder that deep learning alone might give a better results than this hybrid method. So here's a comparison with an equivalent deep learning only method, which uses the same network except for the last layer, which predicts equatorial Pacific SST directly. You can see that both of methods gives comparable scale. Therefore, the hybrid method, we can say that hybrid method provides additional benefit over equivalent deep learning only method, which requires the same amount of training cost without degrading the scale. So the hybrid method is much more interpretable and can track the time evolution. Here's the improvement, special pattern of the improvements at 12 months lead time. It shows the anomaly correlation squared for plain model analog and hybrid method. And here's the difference. So we can see the significant improvement, especially over the central equatorial Pacific. However, the scale does not change significantly on over the western part of the domain, where SST variability is small, and it does not contribute much to the loss function we design. So this method improves more over the region with large SST variability. So here's a seasonal variation of forecast scale. So it shows the, again, anomaly correlation squared as a function of initialization months and lead time. This is for the plain model analog and hybrid method, and this is the difference between these two. Sorry. And the gray line indicates the verification month. So everything along this line is verified in March. This is verified in June. So if we look at this difference plot, we can see overall consistent behavior across the different initialization month. So we do see some reduced scale at shorter leads, but in longer leads, we have an enhanced scale, especially at 6 to 18 months lead time. The strongest improvements are observed for initialization in November to March, which corresponds to borrow winter, with verification during September to March, which corresponds to borrow fall to winter. Once analogs are identified, we can extend the forecast to any field available, which is not possible with a deep learning only method unless it is trained for all of the variables. So this is an example for precipitation forecasting at 12 months lead time, and it shows improvement with respect to the traditional model analog. So we can see that by improving the equatorial Pacific SST forecast, we can also improve the precipitation forecast both inside and outside the target regions, which also supports the ENSO teleconnection impacts. So far, I've shown a result with a perfect model experiment, meaning that all the training and validation and test dataset are from CESM2. But here I'm going to show result using observation data during 1987 to 2020, using the model trained by CESM2. Here are the result with observation. First, we can see that in general, compared to the perfect model experiment, we do see lower anomaly correlation skill in general. For the difference plot, the behavior is different across the initialization month. While there are many initialization months that shows improvement, we do see some initialization months, we do see some reduced skill in forecast, especially initialized in July to September. This may be due to the biases in CSM2, and we may be able to solve this by training with multiple climate models or using transfer learning technique. The improvements are most significant when predicting extreme event. So this figure shows the improvement with respect to linear 3.4 index. The red color indicates a linear condition, and the blue color indicates La Nina condition. And the y-axis is the difference in root mean square error, where positive indicates improvement. So we can see when predicting neutral conditions, the improvements are centered around 0. But when predicting extreme events, we do see consistent improvement. This is the application to observation. And although there are fewer samples in historical data, we can see that most of the extreme events get positive impacts for both El Nino and La Nina forecast. One thing to note here is that linear 3.4 index in the CSM2 is much higher than what historically observed, which might be one of the reasons why it's difficult to apply what we learned in CSM2 directly to observation. So far, I've showed the improvement by deep learning. Next, we will analyze those sensitive regions that produce such improvements. So here are the mean weights of all events in the test dataset. The weights are unitless, so we can scale them such that it sums up to 100%. The sum of weights for each variable is shown in each panel. So we can see overall SST and SSH contribute almost equally, while our tau x contribution is smaller. If we look at SST, the weights allocated to the target region do not dominate the total weights, which explains why we have a reduced scales at shorter lead time. Instead, these weights seems to be connected to Pacific meridional modes or South Pacific meridional modes, which are important precursors of ENSO. We can also see some contributions from Indian and Atlantic Oceans, which supports tropical interbasin interactions. For SSH, the weights are more concentrated over the equatorial Pacific, and these equatorial weights helps to identify the zonal tilt of thermocline, which occur concurrently with ENSO, and also the recharge discharge stage, which is a precursor of ENSO. For wind stress, we can see there's a weight over western tropical Pacific, which may be related to westerly wind bursts. We can also analyze the difference in weights for El Nino and La Nina forecast. So these are the mean weights for El Nino and La Nina. And here are the difference. And what we observe is that in SST, there's a positive difference over the Pacific, meaning that Pacific SST is more important for El Nino forecast. In contrast, there's a negative difference over in the Pacific wind stress, meaning that Pacific wind stress is more important for La Nina forecast. In summary, combining the old and new ways of predicting ENSO makes prediction better and helps us understand how model makes predictions. This method is very useful and we can apply this to various climate forecasting. Thank you for listening and I'm happy to answer any questions.
I have questions. Okay, my first one is, you mentioned, well, you showed that the deep learning, just the deep learning method without the analog aspect performed approximately similarly well.
Yep.
I was wondering, had you looked into like encoding the lead time so that you could have one neural network that can actually forecast across lead times and then explore how accurate it is in comparison?
Yes, that's a very good point, which I haven't done it, but the purpose of comparing with this deep learning only method is just to make a very similar network. I only took the last layer. Of course, I could have done it recurrently so that it can like forecast the evolution. But yeah, I haven't done that in this study yet.
Okay.
It's a very good point. Thank you.
I have another question.
Okay, we'll go to Dan and then we'll come back in the room.
Thanks, Kenya. This was really neat. It was great to see the maps of the weights. I was wondering, an alternative hypothesis to the deep learning finding, particular regions associated with processes. Could it be that it is downweighting places where the model is biased? And so, I guess I was looking at the fact that it seems like in some places the cold tongue the edges of the cold tongue are kind of highlighted as places being upweighted the most. So I was wondering if that might point to, I don't know, model bias or something like that in the extent of the cold tongue.
Yes, yeah, thank you for the question. I think there's also effect of model biases. So these sensitive regions have a same caveat with many, I think, XAI method. They don't actually show the causality. They are just showing the correlation. And these are the regions that helps improve the prediction scale. So even if we see the highlight in some region, it doesn't necessarily mean there's a physical processes associated with it. So yes, I think they are also pointing out to some of the biases. Oh, but one thing note here is that this weight is from the perfect model experiment. So we assume there's no biases in the model.
All right, Kirsten.
Okay. My other question is, now that you have these weights that the neural network learned to predict, I was curious if you could approach this problem where you actually predict the field and then use XAI to kind of look at the initial state and then compare between this interpretable method versus the XAI methods now that you kind of have this baseline for important regions for prediction.
Yes, that's a good point. They are also not only using XAI method, but we can also do similar thing with like traditional methods such as like adjoint modeling. And yeah, I think that's a very interesting thing to look at.
All right, thanks very much for that talk. We have to move on. Let's see, our next speaker is online. I'm going to try to stop share, and then Jacob, you should be able to share your screen.
Okay. Great. Hi, everyone. I'm Jacob Cohen. I'm a grad student at the University of Washington, working with Luann Thompson. And this is a collaborative project with a group of PIs and grad students at the University of Washington, NCAR, and the University of Wisconsin. So marine heat waves are a current hot topic in research, and they're extreme warming events in the ocean that can often drive ecosystem disruptions that have local effects, especially here in Washington on the coast. And these include things like toxic algal blooms, fish and seabird die-offs, as well as economic consequences for fisheries and marine industries. So accurate forecasts of these events will help stakeholders and industries prepare for and respond to these impacts. So to study the predictability of marine heat waves, I'm using hindcast, the seasonal to multi-year large ensemble hindcast, which uses CESM2 and is initialized from a forced ocean sea ice run that is forced by atmospheric reanalysis from JRA 55. And this is the same data set that a couple other speakers have talked about today. And this data set includes 24-month forecasts that are initialized every February, May, August, and November. And each forecast has 20 ensemble members. Marine heat waves are typically defined against a 30-year climatology and threshold. So I'm using all of the initializations from 1989 to 2018 and comparing those to the FOSSI output from 1989 to 2020. And throughout the talk, I will probably refer to the FOSSI output as observations, but it is model output. I have not compared this to observational data yet. So previous studies of marine heat wave predictability have mostly focused on marine heat waves as extreme sea surface temperatures at each individual grid point in the ocean. And when we define events like that, we can use contingency tables, so metrics like hits, misses, correct negatives, and false alarms, just based on at each point, did the forecast predict a marine heat wave? And then did we observe a marine heat wave at that time? And with those metrics, we can calculate predictability skills, such as the symmetric extremal dependence index, which is a common skill metric used for marine heat waves and extreme events. And we see here that in the first lead month, we have pretty good skill globally, and then that drops off pretty rapidly, except we maintain a lot of skill in the tropical Pacific due to ENSO. And this can tell us a lot of information about the spatial variability of our predictive skill, but doesn't necessarily tell us how well we're predicting individual events or whole events themselves. So in my work, I'm defining marine heat waves as spatially connected events and then examining how well we predict those events. So I start by defining marine heat waves at every point. I use a 90th percentile climatological threshold of the sea surface temperature anomalies at each month of the year in the FOSSI output. And then in SMILE, I define marine heat waves again with a 90th percentile threshold, but now the climatology is based on the lead time as well as the initialization month. And this follows the method of Jaycox et al. 2022. So just a quick example of this, I'm just showing here a snapshot of one initialization at one lead time and just one ensemble member. So we start with the sea surface temperature here. We then use our climatology for that initialization month and lead month to get the anomalies. We threshold those anomalies to find each point that is a marine heat wave. And then we pass this map into a package called OSTRAC, which is a marine heat wave detection algorithm that connects those individual points spatially and does some spatial smoothing to identify discrete events in space and time. So at this time step, we see separate events in each of these blue regions. I then pass those events to the method for object-based diagnostic evaluation, or MODE. And this is a forecast verification package that was initially developed for precipitation forecasts to model them as object-based events. And this has also been used to look at atmospheric river forecast verification. And now I'm just applying that method to marine heat waves. So on the left is the same map that we had from OSTRAC, but now we compare that to the FOSSI output at the same time step, and mode matches events between the two data sets. So the colored outlined events are matched for that individual ensemble member, and then the royal blue areas are events in either the forecast or observation that are not matched to the other fields. Quickly, just how we do that matching. Mode calculates what it calls an interest score for each pair of objects, in one object in the forecast and one in the observations. And mode calculates a lot of different attributes. I chose to only use these 4. So I use boundary distance, which is the distance between, the minimum distance between points in each marine heat wave, as well as the convex hull distance, which is the distance between those outlined regions. The centroid distance, as well as something called the intersection area ratio. So this is the fraction of area that is overlapping, and then that's based on the minimum object area. So it can be the ratio of the intersection to either the forecast or observed object. And I essentially combine all of those individual interest scores to calculate an interest score for the pair. And if that pair of objects has an interest score over 0.7, then mode matches the objects. And we get something like this for every time step and every ensemble member. So this is the individual ensemble member perspective. But I also look at a probable marine heat wave perspective, where instead of looking at each ensemble member, I combine all the ensemble members at each time step and select each point where at least 30% of the ensemble members agree that there will be a marine heat wave. And that's what I then pass to OSTRAC for the object creation, and then mode for the object matching. And we see that mode picks out the same 3 objects, but they match the observations slightly better. So we have, again, these 2 perspectives, individual ensemble member perspective, as well as the probable marine heat wave perspective. So once we do all of that matching over every time step, we can start to answer a couple questions. So first, how well did we predict a specific marine heat wave? And then how accurate are marine heat wave hindcasts, which can inform our uncertainties for future marine heat wave forecasts. So we'll start with an example of a specific marine heat wave. Here I'm showing 1 month snapshot of the blob, which was one of the most extreme marine heat waves. It lasted from around 2014 to 2016 in the Northeast Pacific. And as you can see here, it had a really strong signature in the far Northeast Pacific, but really connected all the way down the coast and into the Central Pacific. So we'll look at each of the forecasts that forecast that time step, and then see how those events matched up to the observed marine heat wave. So all these maps will look similar, with the red contours showing the observed marine heat wave from the last slide. The blue area shows the probable marine heat wave, and that's showing the probability based on all of the ensemble members. And then the gray areas show the spread of all of the ensemble member events that matched up to that marine heat wave. So the things to focus on are the location of the probable marine heat wave, as well as the range of the ensemble spread. So 2 years out, we were able to predict a small marine heat wave near the center of, or the high point of the observed marine heat wave. That's likely due to this being a really long-lasting marine heat wave that could be forecast that far out. We'll skip ahead to a little over a year before the event, and this is one of the only forecasts that was able to capture the tropical Pacific warming in the probable marine heat wave perspective, but the range of the ensemble spread is still throughout the entire Pacific Basin. 7 months before, our ensemble spread is now limited to the North Pacific. And then finally, 1 month before, we have a really good match between the probable marine heat wave and the observed marine heat wave. So to quantify the scale of these forecasts, we can look at a lot of different metrics. One is the the distance between the center of mass of the forecast event and the observed event. And we see that as we go to lower lead times, the center of mass is closer between the observed and the forecast event. Another metric is the intersection area. So this is essentially how much of the area of the observed marine heat wave are we forecasting. And as you can see, it generally increases towards lower lead months. We do have this spike at 13 lead months where we did get that tropical Pacific signature as well. So we can extend that to look at every marine heat wave in the record and all initializations and all of the lead times, and start to look at the general scale of marine heat wave forecasts. So one of the metrics that we can look at is called the maximum of median interest. And this is based on the interest scores that I talked about earlier. So we can look at, well, essentially the median object in each field was matched to an object in the other field. So here, when we look at the observations or FOSSI, we're looking at each lead time, how well the median object is matched to a forecast object. So when that number drops below 0.7, then the median object is not found in the forecast, even though it was observed. And we see that, excuse me, quickly, our maximum of median interest drops off below this threshold. So we're not forecasting most of the observed marine heat waves after about 4 or 5 months. However, when we look at this from the forecast perspective, we see that at much longer lead times, the median forecast object is in the observed marine heat waves. So what this tells us is that our forecasts are generally accurate and are matched to marine heat waves, but they often miss marine heat waves that do occur. So we can trust the forecasts, but understand that they're missing events that occur. We can also look at this, instead of with this maximum of median interest, we can look at the fraction of marine heat wave area in each field that is matched to the other field. We see that in the observations, after a couple months, only about 60% of the marine heat wave area is being forecast. However, in the forecast, 80% of the forecast is showing up in the observations. So this is really telling us the same thing as the last plots were. And then finally, we can start to calculate statistics about all of the matched events that we have. So on the left, we can look at the distance between the centroids of all of the matched events. And we see at low lead times, our events are closer together, and then they get further apart. This plateaus because after a certain point, if objects are too far apart, they just won't be matched to each other. And then lastly, we can look at the median probability of the matched events, and we see that they fall off to being very probable, from being very probable to being less probable, down to just about 30%, which is our threshold for the probable events. So I'll leave some conclusions up. This is an exciting data set to now have of all of the matched marine heat waves, and we can use it to look at a lot of different questions around marine heat wave predictability. Thank you.
questions online? Or in the room? Iowa?
I just want to make sure I understand the last point. Do you mean that the SMILE has the statistics of marine heat waves, right? It's just not getting the actual observed ones? Is that, I didn't fully grasp what these diagrams are.
Sure. So like these ones? Yeah. I think my point here is we may have like 10 observed marine heat waves at a time step, and we're forecasting that there will be 3. And those 3 will be in the 10. So we're getting the ones we're forecasting correct, but we're missing, say, 7 of the observed marine heat waves. Does that try to answer that? It's not exactly that, but
so it doesn't produce extra marine heat waves. The ones it gets right, but it's just missing some. Okay.
yes, yeah.
Thanks.
Jan?
Yeah, I guess a follow-up on that. I mean, so do you, and hey, Jacob, nice to see this work. Do you, are the statistics of extreme events at these length scales similar between the model and observations? Maybe that was part of, yes, maybe something I'm reserved from Isla's question, right? Is the model just missing some, or they come with the same frequency and they're just in different places and different times?
So these statistics, and I think I might not have said this, these are for the probable marine heat wave perspective. So these are only looking at heat waves where 30% of the ensemble members agree that there will be a marine heat wave. So at like far lead times, every ensemble member may be predicting the right number of marine heat waves, but they're all in different places, so that very few areas have 30% agreement. Does that make sense? So each ensemble member might have the right number, but our probable marine heat wave perspective will only have like 1 or 2 marine heat waves where we're confident that a marine heat wave will occur.
Okay, but you don't necessarily think that at this resolution and model configuration that maybe, you know, the tail isn't long enough, or there's something about these extreme events that isn't being simulated properly?
There are certain things that I don't think are probably being simulated properly, and that's kind of what we can get at with looking at all the other statistics about the matched events. But we define the events as above the 90th percentile in the model itself. So we're looking at extreme events in that context, so it has its own tail of the distribution, I guess, if that answers your question.
Thanks.
All right, thanks, Jacob. I think we'll move on to Emily Wazinski, also online. So Emily, you should be able to share your screen and go ahead.
Is that working? Okay. Okay. Hi, everyone. My name is Emily Wazinski, and I'm a first-year PhD student at the University of Maryland. My primary research advisor is Dr. Maria Molina, and today I'm going to be sharing some work examining if El Nino precursors are captured by SMILE. I also just want to take a moment to acknowledge all the work of my co-authors, and I'm very grateful for all the input that they've had. So the Seasonal to Multi or Large Ensemble, or SMILE, is created using the Community Earth System Model version 2, or CESM. And this consists of 20 ensemble members, and it's initialized 4 times per year and runs out to 2 years. So the initializations are February, May, August, and November. SMILE predicted a super El Nino event with sea surface temperature anomalies from 2.2 to 2.4 degrees Celsius for DJF in February, May, and August 2023 initializations. And for August specifically, SMILE predicted the index would rise to an average of 2.4 degrees Celsius for DJF, which is similar to the 1997-1998 Nino, which was 2.4, and the 2015-2016 El Nino, which was 2.6. And the SMILE prediction had a bit higher average than the other dynamics models used for El Nino forecasts, but the values were still within the envelope of the other dynamical model predictions. And one of the research questions that has stemmed from this is what conditions caused this? However, the peak amplitude via the Oceanic Nino Index fell short for DJF, and it was recorded as 2.0 degrees Celsius in November, December, January, and DJF was 1.8, but could still update for up to 2 months because of the 3-month rolling mean. And El Nino precursors were apparent from different observational platforms, such as mortar arrays and sail drones, as early as February 2023. And the primary research question that I am interested in is, was SMILE able to resolve these precursors in the February initialization? And I will be focusing on the second research objective for this presentation. So just to give some background, the spring predictability barrier, or SPB, is referred to as decreased model forecast skill when models are initialized from February to May. And the SPB is primarily due to the transitional state of ENSO during the boreal spring. So models struggle to make accurate predictions during this time frame. And it's interesting to note that from February to April, dynamical models tend to outperform statistical models, indicating that the initialization spin-up process in these dynamical models is crucial for skillful prediction. And this is really important because since ENSO is one of the leading sources of climate predictability, it's crucial to not only correctly predict the phase, but also the amplitude for anticipating these global teleconnections. And yeah, even amidst the spring predictability barrier, SMILE did produce skillful El Nino predictions. So we know that the SMILE hindcast set, from the SMILE hindcast set, that SMILE can skillfully predict ENSO. However, we wanted to be careful about the potential for artificial skill to leak into this general assessment because of how the base climatology was calculated. So this paper came out by Risby et al. In 2021 that states that hindcasts may have some type of unrealistic skill because they utilize data that would be unavailable during real-time forecasting, and specifically the climatology to derive these DJF anomalies. So in other words, we wanted to evaluate how sensitive the root mean square error was to the base climatology used for these anomaly calculations. So the top two panels, the red are February forecasts and the blue are May forecasts. The top panels show the climatology that spans from 1970 to 2000 for predicting DJF anomalies from 2000 to 2018. And then the bottom two panels show the 1970 to 2020 climatology that is again predicting the DJF anomalies for 2000 to 2018. And even when deriving these DJF anomalies using the longer climatology period, it does not perform significantly better than when using the 1970 to 2000 climatology, indicating that artificial skill may not be present within this specific hindcast set, and that SMILE does not show substantial artificial skill. So we wanted to clear that up before proceeding with this analysis. So shifting gears a little bit to our observations. First of all, what El Nino precursors are we interested in examining? So the first one that I'm going to talk about is the integrated warm water volume, which is an index of heat content and also a proxy for the ocean heat content. This data that I am using was based on temperature profiles from tau mortar arrays, Argo measurements, and XBTs, which just measure temperature throughout the water column. And also the integration boundary for the warm water volume was the 20-degree isotherm or thermocline. And the particular region that we're looking at is the Western Pacific, which encompasses -5 south to 5 north, and then 120 east to 155 west. So that includes regions of the maritime continent in the west, and then extends into the central equatorial Pacific region. So the warm water volume anomalies these are the warm water volume anomalies plotted for 2000 to 2024. And why is this important to look at in the first place? So the first aspect is the recharge discharge oscillator ENSO theory. So this basically mimics a pendulum swinging between phases, which are equivalent to SST changes and sea level pressure in the equatorial Pacific. So the recharge phase explains La Nina conditions, which is a buildup of warm water in the western equatorial Pacific, And this is fueled by the easterly trade winds and also cool water that is present in the central and eastern equatorial Pacific. And then the subsequent discharge phase explains El Nino conditions. So there reaches some type of threshold at which the cool waters that are present in the eastern Pacific begin to dissipate. And then this weakens or even reverses the easterly trade winds. And then all of that warm water that has been building up in the recharge phase from the La Nina begins to propagate eastward. And then there's also a Walker circulation shift as well. And each of these periods lasts for about 2 to 7 years for each phase. And also another aspect is that ENSO prediction skill greatly increased once ocean heat content was included in models. So this is definitely something worth looking into. And for the 2023-2024 El Nino, there was a multi-year La Nina from 2020 to 2023 that provided ample ocean heat content and warm water volume buildup in the Western Pacific that triggered the El Nino onset and also helped in its materialization. Something interesting is that there was a large discharge in the post-2015-2016 El Nino. And I'm intrigued to see if there's going to be a similar discharge period after this El Nino has concluded. And we can already see that it's dipping below the seasonal cycle a bit. So I'd like to continue to monitor that to see if it reaches the same magnitude as the 2015-2016 El Nino did. So now that we've talked about warm water volume, the next precursor that I'm going to look into are westerly wind bursts. And westerly wind bursts are irregular, anomalous zonal wind perturbations that cause a weakening or reversal of the equatorial trade winds, like I discussed in the discharge process previously. And these events are also known as trigger events that may precede or even enhance El Nino onset and development because they create these large localized accelerations of eastward propagating winds and also currents due to the lack of the Coriolis deflection in the equatorial region. And westerly wind bursts are extremely crucial to understand because they have preceded every notable El Nino on record, but due to the lack of a long observational record, they're quite misunderstood in how their impact and how their relationship with ENSO, and just like how they are related to ENSO is quite misunderstood still. So looking at some of the tropical Pacific observing system WARD arrays, there was a potential westerly wind burst event at the beginning of February, and this plot shows the scalar wind speed in the western equatorial Pacific at both the 0165 east and 0180 buoy locations. So at 0180 west, there was a maximum wind speed of about 11 meters per second, and 0165 east had about 9 meters per second. But this is scalar wind, and that's not really indicative of westward movement. However, we do have the wind direction at these buoy locations. So we did see a wind direction shift towards the east. So we had a westerly wind after this wind speed occurred. And this occurred at the 0165 east buoy. We don't really see it at the 0180 west at all. So now that we've gone over the observations and what we've seen from the buoy locations, our first question when receiving the SMILE February initialization was, does it even predict an El Nino? And it does. SMILE predicted a maximum sea surface temperature anomaly of 2.2 degrees Celsius, which falls into the strong El Nino category. And as from this plot, you can see that there's a quick transition from La Nina to El Nino conditions that occurs throughout the boreal winter to the summer. And something interesting about this figure is that it shows a secondary increase of sea surface temperature anomalies beginning in about July through the rest of the run. That's something that I'm definitely wanting to explore and interested to see if that happens. So now that we have solidified that the SMILE run in February did predict an El Nino to begin with, I was interested to see if there were any of the precursors within SMILE that we saw from the buoy locations. So this plot here is the total horizontal wind speed, and I did a type of buoy proxy. So I sliced the SMILE data to mimic the 0180, 165, and 170 west locations. And we did see an increase in the horizontal wind speed at these locations in the Western Pacific that is very similar to what we saw in the buoy locations. There was a smile horizontal wind speed peak at 0170 west, and there was a buoy peak at 0180 west. So there's about a 10 degrees longitude shift between the observations and the model. And there was also a slightly larger wind speed peak at 12.4 meters per second, and our peak at the buoys was about 11. So now I'm going to look at the derived SMILE wind direction again with those buoy proxies. And for this one, I'm looking at 0165 east because that's where we saw it in the observations. This is very preliminary work. I've only been able to do this with one ensemble member. But this is really promising because we do in fact see a westerly wind that was captured in the SMILE initialization for February. And I think that this is great, but the February westerly wind burst was captured in the February run, again, which is great that it was even captured to begin with, but I'm interested to see how far back this was found within SMILE. Was it resolved in November 2022, August, May, or was it even resolved the year before then? And I think that that's a really exciting avenue for potential work. So now transitioning into my future work, I would like to prioritize computing SMILE ocean heat content because I have not gotten around to do that yet, and I'm really interested to see how the warm water volume anomalies correlate or how they compare to the buoy observations. And I would also like to compute the wind direction across ensemble members. I want to compare the February and May initializations to determine if there were any skill differences during the spring predictability barrier. And then lastly, I kind of alluded to this on the previous slide, but I'd like to investigate how far back SMILE predicts El Nino onset, materialization, and magnitude. So looking at SMILE that were initialized in SMILE runs that were initialized in 2022. So that's all I have. I'll happily take any questions, and thank you for your attention.
Any questions for Emily? Maria? Go ahead, Maria.
Hi.
If you couldn't tell, I'm in the same room. I was curious about your initial thoughts, Steve. If you think that maybe additional initializations of this would be neat to explore to look at like increased lead times and yeah, just interested in your reactions.
So I think it's a good idea to look at earlier initializations. So I'm not sure that we've done 2022 yet, but we're filling in the gaps. So we've got up through 2020, and then we jumped to 2023, but we'll definitely fill that in. I guess my reaction to the westerly wind burst analysis is that I'd be very surprised if we found any predictability of westerly wind bursts in like an ensemble mean sense. You were looking at that single member, and so I think what would be interesting would be to explore the distribution of ENSO developments across ensemble members, sort of in relating that to the magnitude or frequency of westerly wind burst events, right? So just kind of basically looking at how that contributes to spread in the ensemble as opposed to being a key component of the predictability.
Yeah, that's really interesting. I'll definitely consider doing that and look into that. Thank you.
Yeah.
So I have a question as a follow-up about the westerly wind burst, and this is Kathy Pigeon. I'm curious about westerly wind bursts from a perspective of duration. Like random westerly winds happen all the time and don't really do anything if they don't last a little longer than sort of really just a short time period. Did you look at anything to do with the duration of the westerly wind bursts?
Yeah, that's a great question. I have an extra slide on this. That's awesome.
Yeah, we did not coordinate on this, just so you know.
So yeah, the westerly windburst definition is definitely not standardized across the literature. I found that some people, like the first bullet point, had it lasting 5 to 20 days, but then another person had it longer than 2 days, and it has to have a certain, it has to span a certain amount of degrees in longitude, and then it has to reach a specific threshold. So yeah, I think that looking at the duration of them would be, yeah, the duration and intensity are definitely going to be huge factors, but I'm not entirely sure. Like, I think that the definition right now is not super helpful. But yeah, maybe looking across the ensemble members and kind of seeing like maybe what the average, like looking at this graphic, like we have an increase in like maybe looking at how many days this spanned, and then for like a specific ensemble member, so maybe like 4 days, and then another ensemble member had like 6 days. So maybe seeing like what the average was, and then what the different wind or the different wind speeds was. Yeah, I'm not entirely sure, but I definitely think that them happening in February or February or March is very important. So I'll definitely be targeting those because those are considered to be more of the trigger events than just like the anomalous like westerly flow like during the summer. So I think that that is what I'm targeting for sure, is the ones occurring then.
Yeah, thank
Did
you.
that answer your question?
Yeah, it did, and actually this is nice to see how long they last in this particular picture. And thinking about the February one that has sort of an extended period. And maybe, yeah, you're right, the definitions of westerly windbursts are all over the place, but you could be the one to help us figure out something good.
Yeah, hopefully.
Emily, I just wanted to make one other comment. So as part of work on NOAA's model diagnostic task force, I think her name is Kelly Delaripa. She works with Charlotte DeMott. They're developing a diagnostic for evaluating model westerly windburst, sort of frequency, spatial structure, magnitude, and its relation to Kelvin wave propagation. And they've got a prototype of that, and it will be coming out pretty soon. And it's designed to be applicable to multi-model. So it could be interesting to apply a tool like that to SMILE, and just look at the statistics of westerly wind bursts as a function of lead time. So it's just something to look out for in the future.
Yeah, thanks for the heads up. I'll definitely check that out.
All right, thanks, Emily, and we'll move on to our final speaker, Yongyup Kim. Are you with us, Yongyup? There you are.
Yes. Okay, can you see my screen?
Yep, and we can hear you.
Okay. Hi, I am Yongyup Kim, currently working in the IBS Center for Climate Physics in South Korea. We have developed multi-year climate prediction system using CESM 2 last year. One of our team member, Junie, also presented about our new system in ENCA February. Instead of introducing all the results here, I will introduce the configuration of our prediction system and some basic skills today. Here are some key prediction systems associated with our new system. In 2018, ENCA developed decadal prediction system. The name is CESM DPLE, decadal prediction large ensemble with CESM1.
Hold on, Yongyup. We're not seeing the progression of your slides.
Yongyup, could you hit play? Can you press play on your side?
Okay. And
press play up on the top bar. Top
You,
bar.
yeah, okay. And you can see this, right? Yeah, this kind of story is okay.
It would be, if you can hit the play on the top bar, it would be easier for us to see.
Yeah, go up to the top.
Mm.
Play.
Very top.
Mm-hmm.
Very top.
Yeah. Great.
Yeah,
Okay. Okay. I guess it works better. Mm-hmm.
Okay, go for it.
Okay. Yeah. Yeah. And yeah, at the time, the CSM DPLE utilized large ensembles concept to the initialized prediction system. So, and then next year, Chikamoto et al. Also developed decadal prediction system, but he adopted anomaly assimilation to trying to minimize the drift in long-term prediction. Over time, in 2022, ENCA developed new seasonal to interannual prediction system, SMART, as you know. But SMART consists of 2-year forecast focusing seasonal predictability. So we developed a new system with 5-year forecast to assess the multi-year predictability using CESM2. Since we simulated long-term forecast, we had to consider model drift, so we adopted anomaly assimilation concepts such as second prediction system of Chikamoto. Our climate prediction system was conducted following this step. Firstly, we regarded CESM2 large ensemble data as uninitialized run to save computing resources. We set 10 members as uninitialized run, and they were also used for initial condition for assimilation run. And we assimilated 3-dimensional anomaly temperature and salinity to avoid initialization shock with 3 kinds of observational data set. In the assimilation process, we didn't assimilate it in ice region due to the heat imbalance in the ice model. We assigned 10 members for 1 observation data set. So we have total 30 ensemble members of assimilation data, but assimilation with ORAES4 is for just validation. So other 20 assimilation members were used for initialized hindcast. So we conducted 5-year hindcast for the initialized years from 1960 to 2021. So total simulation every January 1st. So total simulation years are 6,200. We can do typical predictability studies with this initialized system, but the keywords for our system is with CESM2 and the long-term hindcast, 5-year hindcast, and then anomaly simulation to minimize the drift. And then we just initialize ocean, so it's good to explore predictability sources from ocean. As I said, we implemented anomaly assimilation. In the figure below, 2 green lines are different observation data. They show different variations. That means observational data also have uncertainty. So we try to assimilate 2 observational data sets to consider uncertainty among observation. Circles and cross marks are assimilated observation data set. We extracted and removed external forcing signal from SVD analysis between large ensembles and observations first, and then added external forcing signal from large ensemble. So these bias-adjusted data sets should have internal climate variability from observation, and with external force trend from large ensembles represented by gray line. Yeah, and red line assimilation data is our simulation data. It follows bias-adjusted observation data very well. And blue line, the hindcast, also shows variation without severe model drift. And right column shows forecast drift normalized by RMSE of large ensembles for radio 1, 3, and 5. Model drift ratio is smaller than 1 over the entire forecast period. That means model drift is suppressed in our prediction system. From this slide, I will show our multi-year prediction the anomaly correlation scales, ACC scales for atmosphere, land, and ocean variables by classical way. First variable is surface air temperature. The first column is ACC between accumulated data and hindcast, which is generally called as potential predictability. First row is lead year 1, and second row is lead year 2 to 4, scale of moving average variables across the forecast second year to fourth year. As we know, it shows pretty high scale even for lead year 2 to 4 because external force trend has high contribution in prediction scales. The second column is ACC between observation and a hindcast, which is actual prediction scale. We use the ER5 reanalysis as observation for convenience. As we know, actual prediction scales of surface temperatures are high. It is not surprising. And third column is the typical data ACC. That means subtracting uninitialized scale from initialized scale. It means potential scale improvement by initialization. And Eastern Pacific shows a high improvement for lead year 1 because scale in this area is dominantly driven by ENSO rather than warming trends. Around Labrador Sea also show high improvement even for higher lead year because ocean-originated multi-decadal variability is more dominant than a warming trend. First column, scale improvement, but for the actual prediction scale also shows similar pattern with potential improvement. Next variable is sea level pressure. We can also see high potential predictability and actual scale for lead year 1. And scales also stand in many regions for lead year 2 to 4, but potential predictability and actual scales are not exactly the same pattern. We can check potential initialized impact is high in Indian Ocean and Western Pacific regions, particularly in the maritime continent. Actual scale case shows similar pattern, but a little bit degraded. For lead year 2 to 4, initialized improvements are not promising. Lower values might not be significant, but it needs more deep analysis for finding multi-year predictability. Today, most of atmospheric and land variables don't show promising results in multi-year prediction timescale, but it makes sense if we consider their high frequency variability and general predictability timescale of them. Here is the precipitation result. Precipitation roughly looks like high scales over the world, but it doesn't have any scales in central area of large continent in northern hemisphere, such like Eurasia, center of the Eurasia and North America. I guess oceanic initialization is not much effective for the region far away from the ocean, and high frequency variability of precipitation also makes prediction hard. In southern hemisphere, ocean regions are larger than land regions, so ocean initialization might be more effective than northern hemisphere. For lead year 2 to 4, polar regions show high scale, but initialization improvements are almost zero, which means that those high values come from external forces. We used GPCC observation data to consider data uncertainty and longer period than GPCP. So we just evaluated land precipitation for actual scale. Some tropical to subtropical regions show considerable value but lower than potential scale. We can guess that initialization was effective for land precipitation in Eastern Africa and Australia, Western North America, and Eastern South America. And next variable is one of the land variables, total water storage, TWS. TWS also shows pretty high scale over the world. TWS is highly associated with precipitation, but it has higher predictability by damping process. And data ACC initialization improvement by is promising in all the southern hemisphere, but it doesn't effective in Sahara dust, India, and Siberia, and some regions in North America. Similar with former variables. TWS has high scale in some regions for radio 2 to 4, but it is from external forcing, so data ACC is almost zero over the world. Some local regions show high values, such like Northern Australia, Gulf of California, and Western Sahara and Horn of Africa. But yeah, those regions, yeah, it's too local. But yeah, those regions, I guess those regions need more analysis. And some regions have actual prediction scales for radio 1, but it loses all the scales from initialization for radio 2 to 4. The next variable is gross primary productivity. GPP also shows similar pattern with TWS because base station and GPP are highly associated with TWS, but it lost all the scales from initialization for radio 2 to 4. Predictable regions and mechanisms are mostly overlapped with TWS for potential predictability, but show a little bit different patterns over Siberian region. It shows high scale over the Siberia, but most scale comes from external forcing. So data ACC for actual scales are almost zero for radio 2 to 4. And next variable is fire bond area. We also evaluated carbon loss by fire, but bond area is a little bit better than carbon loss variable. Both variables have large uncertainty in observation, so it was hard to evaluate actual scale. Anyway, these fire-related variables are related to vegetation and soil moisture, so it also shows similar pattern with former land variables. Radio 2 to 4 data ACs are still insignificant. Next one is oceanic variable, sea surface height. Ocean model in CESM2 is not non-Bushnell model, and it doesn't consider all the sea level rise by mass changes. So we evaluated scale for detrended sea surface height. Since we initialized 3D temperature and salinity, so density was changed and it makes SSH changes for bottom pressure balance. So potential predictability is higher in most of the regions. And initialization scale improvement is also high over the world for radio 1. Actual prediction scales are also high in most of the regions. Actual scale improvement is also promising for radio 1. For radio 2 to 4, tropical Atlantic, Western Pacific, and Indian Oceans to show high potential predictability and actual prediction scale. In same region, scale improvements also show promising value. SSH show promising multi-year prediction scale due to the slow ocean dynamics as we expected. This is the Rust variable, marine net primary productivity, integrated from surface to 100 meter. For radial 1, it shows promising value for potential predictability over the most of the regions. For actual scale, observation period is too short and it has large uncertainty. So scale looks like mosaic pattern because it is largely driven by artificial trend due to the extreme peak because of the short period. Although it shows promising value in some tropical to subtropical regions. For radial 2 to 4, subtropical regions show high initialized scale, so I am focusing on the predictable mechanism of marine MPP and other business variables in multi-year timescale, but I will skip the detailed explanation of the detailed mechanism for today. So this is the summary. We newly developed a multi-year prediction system and assessed basic ACC scales of some variables. And atmospheric and land variables, which are mostly driven by atmospheric white noise, showed low predictability, but ocean variables showed high predictability compared to the atmospheric and land variables, which this high predictability is driven by slow ocean dynamics in multi-year timescale. And here is the list of the ongoing sub-project. Voided sentences have preliminary result and love story, and the others are started in a few months. More work is needed to develop a deeper process level understanding of the scale patterns shown. This huge data set needs collaborators who are interested in predictability work. And I am writing a discussion paper for this work, and we are planning to share data publicly after the paper publication. Actually, my postdoc contract is until this August, so I hope to submit a discussion paper in the first half of this year, and data would be open this year, I guess. Yeah. And if you have any question, feel free to contact me anytime. Yeah. Thank you.
Any questions in the room or online? Sanjeev.
Yeah, this is a great presentation. I think you already mentioned that you did not initialize the land, and you assess the skill over the land quantity also. So if you compare this Smiley system with the Smiley system that Steve has, where he has initialized the land too, so whether you would expect a more skill, or is there some usefulness in comparing two of the Smiley system, at least for the first 2 years, and assess the impact of the initialization method or the component initialization to learn something new?
Okay, it's a really good question, and actually, our team also thinks about this kind of subjects. So, this February, actually, Junie went to Anchor, and then I heard that she discussed the collaboration with Anchor for the comparison of our system and smart system, because both of system have the different initialization approach. And I guess our system is focusing on the long-term predictability. If we evaluate the sub-seasonal to, I'm not sure for seasonal, but if we evaluate the sub-seasonal predictability, and I guess our system doesn't show promising result because we didn't initialize the land and atmosphere variables, I guess smart is better than our system in subseasonal predictability. But in the multi-year predictability, we try to minimize the drift, and then we would like to believe that our approach make kind of, if we did the anomaly assimilation, I guess there is kind of the artificial noise from the drift can be removed. Yeah. So I guess our system can show the promising result in multi-year predictability. Yeah, but we are not sure. Actually, we just surface temperature for say seasonal prediction, but the small, and then our system showed the similar scale, I guess. Yeah, but a little bit different in patterns and some detail values. Yeah. Okay. Thank you.
Yeah, thanks, Yong. Any other questions? If not, we'll move on. So you can stop sharing.
Okay.
All right, next up is the working group update. Sasha helped me put together the slide deck, and then I was adding stuff that seemed like I should probably explain, so I'm up here giving this update. We always like to start with just a reminder of sort of some legacy data sets of the working group that are available. They've got references. These include CSM1, S2S, and seasonal hindcasts. We have, of course, the decadal prediction large ensemble using CSM1. And then most recently, we have put out the CSM2 S2S set for both CAM6 and LACM6, and the SMILE data set that we heard a lot about today. All of these, actually, I'm not sure all of them are available from the working group website, which is listed up at the top here, but you can get in touch with us if you would like to access this legacy data. And perhaps more interesting is the new data sets that we have coming out soon. We heard from Yaga and Kathy about these perturbed initialization CSM2 S2S hindcasts. We now have a reference for that, Richter et al. 2024. These should be coming out soon, perhaps by the June workshop. We have been participating in an international collaboration with Clivar's Tropical Basin Interaction Panel, TBI, to run hindcast pacemaker experiments. And so we have completed a preliminary set of those that are relative to the SMILE control, initialized in February only at this point. And I'll show some preliminary results from those pacemaker hindcasts. An exciting new data set is a new decadal prediction data set using CSM2. So this represents the decadal extension of SMILE November. So we took those 24-month hindcasts and extended them through 122 months, so full decadal lead times. And this simulation data set will then span 1958 to 2020, and we'll have a 20-member ensemble. And then I'm also going to mention a new experiment that we've recently run, which is sort of probing initial condition sensitivity in our CSM2 S2S set by swapping in DART atmosphere initialization And Sasha completed these runs pretty recently, and we have some early results to share. So these are all data sets that will be coming out probably over the next year, if not by June. All right, just a little bit more depth, starting with this CLIVAR TBI coordinated experiment idea. There's a group of us that have come to consensus on an experimental design in which we restore prognostic SST within these tropical regions in the Atlantic, Pacific, and Indian using a common region mask, a common SST target data set, and sort of a common protocol for restoring strength. And so the ESPWG has completed these for February initialization. And I'm just going to highlight one result from the TBI Atlantic experiment. This is where we've redone SMILE, but with anomaly restoring in the tropical Atlantic. And then we can look at how the SST skill compares to the SMILE control. And that's what I'm showing you in these plots. The ACC skill as a function of forecast lead time on the x-axis for 3 different SST regions, Nino 3-4, Atlantic 3, the main development region in the Atlantic, and then the Indian Ocean dipole. The TBI experiment is in blue, so you can compare that to the black and gray, which are, the black is the full SMILE, and then the gray is the resampled 10-member SMILE. So what we see in the Atlantic pacemaking experiment is that by design, our skill for these Atlantic indices is near 1. And then we can look at how that improved performance in the tropical Atlantic region impacts other basins. And basically the take-home point from this experiment is that it does not really improve our year 1 El Nino forecast. You can see that the DJF ACC score is basically the same as in the SMILE control. It's only in the ENSO decay phase that we really see an impact of improved skill in the tropical Atlantic. And then another result here is that a lack of sensitivity of our skill for Indian Ocean dipole to any restoring in the Atlantic. So these are the sorts of sensitivities we can start to tease apart with these different experiments, and we're just starting to do that. And we plan to contribute to a joint paper that will outline these experiments and probably show some early results from them. The other new experiment that I mentioned is the CESM2 S2S hindcast set using initialization from a DART reanalysis data set spearheaded by Kevin Rader. So in the default S2S set, the atmospheric initial conditions came from NCEP reanalysis. We're now swapping in this in-house DART reanalysis that uses the CAM model that's also used in the S2S experiment. We kept the land initialization the same and the ocean initialization the same, just to highlight the impact of a change in the atmospheric initialization. And so Sasha made this plot showing standard skill. I think this is overall the extended verification window from 1999 through 2020. We didn't have the reanalysis going back as far as 1999, so we're looking at sort of a 10-year window for verification of the new DART experiment, and then comparing that to our control that's verified over the same window. And then on the right here, we see the skill difference maps for surface air temperature globally, and it's a mixed bag. There's quite a bit of area with skill improvement over mid-latitudes, but also some large areas of degradation, notably over equatorial Africa, that we think may be related to a mismatch between the new DART atmosphere and the sort of legacy NCEP forced land initial condition. And so we think our next step will be to repeat this experiment and then use the Dart land initialization as well. Kind of get a feel for, how the combined Dart state might improve S2S skill. So this is work in progress. Another new data set I just wanted to show a teaser from is this new CSM2 decadal prediction hindcast set. I'm showing you here differences in forecast year 1 through 5 annual mean precipitation from the new 20-member CSM2 DP, our current workhorse, the CSM1 DPLE that has 40 members, and I'm differencing these without trying to account for differences in ensemble size, and even without doing that, we can see widespread improvement in precipitation skill in the new CSM2 decadal hindcast set with some really interesting improvements over west coast of North America and the Sahel region of Africa. Overall, it looks like we're seeing some real skill benefits that we will then have to try to understand, because we've not only changed model physics, but we've also changed the initialization methodology. Not only how we initialize the ocean, but also in CSM2DP, because it is an extension of SMILE. We're also taking care to initialize the atmosphere and land, and so a lot of work remains to be done to kind of do some quality control on this data set, assess some basic skill metrics, and then start to understand what we're seeing. So since we now have a CSM2 decadal prediction hindcast set, we were able to submit a decadal forecast this year to the WMO Lead Center that is organized at the UK Met Office. So we just heard earlier today about SMILE, initialized on November 1st, 2023. We've extended that out 10 years, and I'm showing you what our new decadal prediction system says the outlook looks like for forecast years 2 through 10. So basically, this would be 2025 through 2033. And what really pops out is this suggestion that we may be looking at a IPO plus sort of transition into the future with this warming in the eastern equatorial Pacific. Corresponding shifts in precipitation, including an extended weakening of precipitation over northern South America, and then a pretty strong AMOC weakening coming up in the next 10 years. So this forecast will be included in the 2024 edition of the Global Annual to Decadal Climate Update that is currently in preparation. Okay, I wanted to put in an advertisement for this Earth System Predictability Across Timescales workshop that Yaga is organizing. This is going to be April 10th through 12th of this year. Take place at Center Green in Boulder, but virtual attendance is an option. And this will really be a key opportunity for working group members to provide feedback that will guide NCAR's kind of overarching plan for Earth system prediction. So I encourage everyone to register for that. And then finally, before we get into discussion, I had a couple points to make. First is that we have plenty of core hours remaining in our current CSL allocation that's going to expire at the end of October this year. So please share your ideas, and in particular, if you think that you have shovel-ready experiment and you need compute resources to do it, that is also relevant to the working group, then send a one-page proposal to Kathy and I, and we'd be happy to share some of our remaining allocation. I mean, we can also come up with ideas, and so here's just a short list of some ideas of what we could do in the next 6 months. We could extend our decadal prediction hindcast set to 20-year lead times. Some groups are doing this, and I've been contacted by one of the leads of the EU Aspect project that wants to look at 20-year initialized predictions. Would we be able to take part, and we could potentially do that if we put resources into that. We could, if there's enough interest, expand the TBI pacemaker set, maybe look at new start months rather than just February. We could expand upon this exploration of the added value of initialization from data assimilation, in particular from DART, that uses the models, that gives us a state reconstructed for the models that we're using in our systems. So I've already mentioned that we really would like to do the experiment with land initialization from DART, but are there other ideas where we could kind of make more headway down this path of really getting some solid answers to what the benefits would be of putting more kind of effort and resource into data assimilation for initialization. Some people are planning to do S2S with online nudging, so Judith is here. I think they have plans to proceed with that and use up some allocations, so we've kind of got that covered. But as we saw earlier today, coupled model bias is a real limiting factor, I think, in our CESM prediction systems. That we can do this two-tier sort of approach, or we could do more to explore online bias correction, and we've talked about that, but maybe that's something that we could do more concretely, not only for S2S but also for seasonal to decadal timescales. A couple other topics. The atmospheric forcing data set for ocean and sea ice models that we've been using very effectively for SMILE and CSM2DP has been discontinued as of February 1st of 2024, and so we can no longer do real-time updates of either SMILE or CSM2DP, and we need a new solution. So, if we're interested in doing real-time, and we saw how that can be really interesting when there are big events happening, to be able to explore that using initialized prediction experiments, then we need to come up with a new solution. So there are plans underway to develop a new ERA5 based forcing, but it will take some time to develop that. So I can already say that's one advantage of the South Korean system, is that they're not reliant on these reanalysis products. They are reliant on ocean reanalyses, but they have a method for initializing their system that potentially they can keep operating in real time. It's probably a little bit early, but we can already start thinking about sort of big ideas for the next CSL proposal that we're going to have to write over the summer. And so, I encourage people to think big, and then get in touch with Kathy and I. And then finally, this still hasn't been confirmed, but there's possibly going to be a large international workshop on seasonal to decadal prediction at NCAR in November. So I just wanted to put that on people's radar.
Who's organizing that?
Me and John Robson. So, this is something, an idea that came out of the Decadal Climate Prediction Project, DCPP. Kind of wanted to do another one of these large workshops. We've had them in the past. We had one in Boulder, I don't even know how many years ago now.
2016.
2016?
2016.
And then there was one in Toulouse, I think after the Boulder one. Anyways, seemed like we were due for one in particular because we're gearing up for CMIP7, and we'd really like kind of broad community feedback on what we're going to propose as far as decayal prediction experiments. And this is kind of an opportunity to do that and then write our protocol later this year. So with that, I'll open it up and ask for feedback and ideas.
I was just wondering about the DART versus the regular ones. It seemed like there were big differences in the Southern Ocean, although the Southern Ocean wasn't really on the plots, but the edge of it was. I'm just wondering, is there any reason not to also compare with the JRA 55 SMILE and ERA 5 SMILE initializations? I wonder if NCEP is a bit weird in the Southern Hemisphere or something.
I don't know that we have those for S2S, right?
Yeah, I guess my question is it any different from what's different from the SMILE?
Right.
Is something else done differently in S2S versus the SMILE?
Yeah, so this skill metric here is computed from the weekly initializations
Oh, okay.
for winter time. I don't know if that's, yeah, season is DJF. So S2S is always weekly initializations over this 10-year time period. So we can't really do an apples to apples with SMILE.
We could do it for the 4 dates we have, I guess, over those time periods.
We could, but then we have a sample size of 10.
Yeah.
I mean, I think it would be easier to, just redo with the JRA 55 initialized atmosphere, right? Just kind of really fill in the matrix of different initialization options for S2S, which these experiments are relatively cheap, right? We're doing Hindcast with 11 members, but compared to SMILE or decayal prediction, these are economical experiments. So we can fill out a matrix of sensitivity to initial condition source.
Yeah, I know that NCEP has storm track trends over the last 4 decades that don't look like other reanalyses, so I just wonder if it's just different in the Southern Hemisphere, and whether having a broader test of DART against the other ways we initialize.
How do you gauge realism in the Southern Ocean? Because you're just comparing reanalyses with each other.
Yeah, you can't say which one's real, but NCEP is pretty old, right? And ERA 5 is, I don't know, you think it might be better.
Maybe it is, I don't know.
I'm confused. So this is the old NCEP reanalysis. This is not like a CFS reanalysis? It's like
No, this is NCEP CFS, sorry.
CFS V2. Oh.
CFS V2.
Yeah, well, definitely, the reanalyses are all kind of different in what they do in long-term trends in the Southern Hemisphere, so I do think it would be interesting to compare.
Yeah, we could compare, how much of the skill is coming from a trend component, it's not clear because, we're not really looking at a very long time period here. I can't see online, so I can't see if anyone online is
Yeah,
one.
so there's a comment by Kevin Rader, says, how real time does the replacement for JRI 55 need to be? There's infrastructure in DART to provide surface forcing from Cam 6, but it would take some time to get the observations and run the assimilations. Real time, I don't know how real time does it need to be, I don't know what that means.
Well, Yaga can answer, like within 5
We need
days.
to run a Tuesday forecast. It needs to be submitted to NOAA by Thursday AM. Tuesday or Monday? Now I lost track. Monday. So we need to run Monday's forecast. Usually we run it on Tuesday, just so we have slack, and it gets submitted to NOAA on Wednesday. So we have about 48 hours.
Yeah, so we can't probably rely on you, Kevin, to do that every week, unless, that becomes a priority for the organization, then we can.
2 sets of hands online. Richard Burke first.
Go ahead, Richard.
Richard, go ahead, we can't hear you if you're speaking. You may need to unmute.
How about this? Can you hear me now?
Yes.
Yes.
Yeah, I'm a statistician and I'm pretty new to this subject matter. And my question is, if somebody wanted to really get into the weeds on the equations and kinds of equations that are used in any of the modules, where would you look?
Kevin Trenberth has a book, right?
Okay.
About climate modeling. Is that what you mean inside the climate model itself, or?
Yes, for example, if you use stochastic differential equations rather than partial differential equations, where would I find that information? I looked on the internet and some of your documentation, and that was not made clear to me.
There are some review papers for CESM releases, and you could look there for references as a starting point. You haven't already.
Okay.
So I think the most recent one is Danabasoglu et al. 2020?
Okay, that helps. And someone mentioned the book by Kevin.
Trenberth.
Yeah. Would that do?
That's more general about like climate modeling in general, as opposed to particular to CESM.
Yeah. Okay. Well, I can certainly check those references then. If I can find some stuff there, that'd be great. Thanks for your help.
Next hand was Maria.
Yeah, Maria.
Hello. I had a quick question about the S2S runs. Just thinking about if we are using or training on, this is a machine learning based models, if we're training on the hindcast set and then doing inference on the newer real-time set, how different are those? And I see on the slide here you have the dark atmosphere, but I was curious about the more like the regular CESM2 S2S hindcasts run in real time.
Yeah, so we have stopped the real-time runs for the reason that I mentioned, which is that we no longer are able to update our ocean state, right? So the current CSM2 S2S set had been using ocean initial conditions from JRA 55DO forcing, which has been discontinued. And so we're stuck as far as real time at this point.
Okay. Sorry, I missed that, Steve.
So to comment on that, I mean, so there's the C-Force project that will bring ERA 5 as a kind of supposed to be the next generation of JRA for ocean forcing. So is the plan to, as Isla mentioned, kind of rerun experiments with ERA 5? And I guess I'm wondering too, is there a transition to CESM3 MOM6 that might happen at that same time? Or what, are there thoughts about how to stagger those products?
Great questions. I guess one thing I was thinking, and I mentioned this to Gokhan, is you don't have to start by reinventing the wheel with the ERA 5 forcing. Like I would like to download ERA 5, get it here, and just re-reference the climatology to JRA 55DO, which we've already established as a pretty reliable climatology for ocean models. And you see variability from ERA 5, and just see if we can, get a similar ocean state and see, do some tests and see, does it give us similar prediction skill for S2S and SMILE? If so, then we've got, a temporary path forward until C-Force comes up with its ultimate product. So that I see that as maybe something that we want to do and start exploring. That could get us back into the real-time game if it were successful. Or we could explore, other ocean options. So Yaga, you've been doing these S2S runs with like a Mara-forced ocean, right? Where you're nudging the, I think you were nudging the atmosphere to Mara reanalysis.
Wacom, yeah.
Yeah. And, you know, we're not sure if that would work for the longer timescales because it introduces drift in the ocean, which is the whole reason for, you know, omit sort of refined forcing products. But yeah, we're kind of searching for a temporary path forward and trying to figure out, you know, to what extent should we just move to CESM3 or explore these issues, kind of given the fact that we have all of these new control hindcache using CSM2. To me, it makes sense to do that exploration in CSM2 space. But, you know, I think, you know, for as far as writing the next CSL proposal, you know, we are going to put in CSM3 hindcache, and, you know, there's going to have to be some kind of coordination with OMWG on that. You know, who does what, and that it's all TBD, I think.
As a word, so these, we haven't written a proposal yet, but we are testing on derecho an online bias correction based on nudging. So it's not actually nudged forecast, it's coming up with an online bias correction. And currently, Will is spearheading to have one that's machine learned as opposed to from the nudging tendencies. That's something we could put into the CSL allocation with a machine learned model error parameterization. I'm right now writing a proposal to extend it to the ocean, which would be then nice if we also have ocean nudging and really truly coupled nudging tendencies and online bias correction. So these are definitely some things we can iterate on, and could take the lead on it, pending resources.
Can I ask for clarification? When you say online bias correction, you mean the model is learning as it goes, it's learning to correct as it runs, as opposed to a post-processing bias correction? Is that what you're describing?
So yes,
Okay.
yeah. Mhm.
Just want to make sure.
And one is just by reinserting nudging tendencies,
Right.
the statistics of them.
Mm-hmm.
And then what's the stuff underway is to use a CNN and really learn the model, learn the nudging tendencies as function of the state, but you no longer have the nudging tendencies. You really run it online in the.
So it's constantly updating itself as the model runs more and more, it learns more and more about it.
Yeah, it's not online in a machine learning sense.
Okay.
Yeah. So one thing I would really like to see, and Dan, we talked about it, is for me, it's really not clear, for example, if ocean initialization in a model with initialization shock, if that is, to which degree this is really limiting the skill in seasonal to decadal forecasts. And I think it would be really nice to design some sort of perfect model ensemble. Ideally, we would have ocean reanalysis, but if we don't have ocean reanalysis, you know, some sort of perfect model ensemble to really look at what is the potential skill if we were to initialize the ocean on its attractor rather than off the attractor. So I don't have an experiment set up in mind I can propose, but I think it would be really interesting to do a bit more. I think we learned a lot from sort of these perfect model ensembles, or Yaga's one where you put a climatology in and then you can look at those effects. I think sort of an extension to that would be really nice to see how longer would be the potential predictability if we were able to initialize on that tractor.
I mean, don't you think that what Yang Yub showed is sort of
I need
going towards
to
there?
look more. It took me a while to realize in his talk that he was actually not looking at SMILE. I had assumed, yeah.
Right, but they're, it's a similar
So they do-
experimental
Yeah.
setup, but
Right.
they're initializing from a coupled model state. So they've got, an atmosphere, ocean, land, sea ice that are all in balance, and they're just nudging ocean anomalies into the ocean. So in that sense, they're, by design, eliminating initialization shock and model drift. I think that's their point, is that, they're looking at what are the benefits of initializing without those things.
Yeah, I will follow that work.
And I like the idea of trying to come up with a coupled, way to reconstruct coupled states that are in balance. The Holy Grail is coupled DA. I don't think anytime soon we can think about using that for decadal or for verifying decadal hindcasts that go back to the mid-20th century. It's just, it doesn't sound tractable to me. I don't know, what do you think, Dan?
We've outlined the steps before, right? And it's kind of a question of where this organization would like to prioritize. And, I'm holding out and trying to invest a lot in the Earth System Predictability initiatives at NCAR. And so I think, that's one direction, is to do coupled DA on long time scales that we've talked about. Or, it may be that we get more traction doing more of an atmosphere-focused data simulation, for S2S on shorter time scales. Either way, too, I think it would be good for us to have strategies for DA, but also for bias correction, right? I think right now it's an exciting time, right? We're discovering like these AMIP-style things that can help us deal with some of these biases, but we know that one of the reasons that data simulation might fail, even though it should be the way to go, is if the model is just fundamentally biased, right? We can pull the model towards the data, but if we're pulling it off of its attractor, we're kind of out of luck, right? And so I think we need to have, solid strategies that we can pursue in both of those directions. But to answer about the coupled DA, we need people for it, I guess.
Yeah, and just, I think Yong-Job Kim, right, he was starting from this, from a reanalysis from a coupled state, but the fact that your model is off the attractor from your ops, I think was maybe not addressed in his work, what Dan just said.
I didn't quite follow that.
That you're off the attractor, that our model just, in the atmosphere, right, if you initialize from a reanalysis, or from an analysis, and you initialize your atmospheric model, then it'll go into its own attractor, right?
Right, but they're not initializing from that.
Okay, yeah, okay, then I need to look at that.
All they're doing is running, lens 2 members with ocean anomaly nudging.
Okay.
So I think I sort of have two things I want to say. One is that one of the things I really like about the Earth System Prediction Working Group and the experiments that have been done is that, this constructing of data assimilation, and I feel like there's it gets deep into the weeds of engineering of a system, and there's a lot of that going on, and I don't mean to dismiss its importance, but I feel like there's something really unique here with the experiments that are being done with this model that no one else is doing. Whereas there are a lot of people working on the data assimilation problem. And so not to say that I don't think that's important, I think we have lots of avenues to explore that, but I don't want to lose sight of these really interesting unique sets of experiments that are being done that allow us to answer really key questions about predictability that I don't think we can do otherwise. And so, my own personal opinion is that I would hate to get off into the weeds of data assimilation because we can do a lot without data assimilation that seems to be telling us a lot of scientific information.
Yeah, I agree with you. I like the fact that our systems are so nimble and we can do experiments without just the huge kind of overhead of a data assimilation effort that will slow the gears down. On the other hand, we are using data assimilation right now. We're just using someone else's.
Right.
We're using ERA5 or JRA55. I said at the workshop the other week, it'd be really nice to have our own in-house atmospheric reanalysis. And Kevin has provided us this in 2011 onwards, but if we had that back to 1958, we would be using that for decadal prediction experiments, because it would be done with CAM. We'd have a way to, initialize an ensemble. We would then make the modifications we need to make to get a good looking ocean in sea ice state, and we'd be able to feed back to the people who are doing that atmospheric reanalysis. Look, it's way out of balance. And, feedbacks that we can't do right now, because we don't deal with the people creating these atmospheric reanalysis, but for me, that's where we should go.
Then I want to raise one other issue that has not come up, complete turn from discussion about assimilation. There are all of these machine learning numerical weather prediction models that have come online recently. People are starting to push them to longer timescales, and that is going to happen rapidly. When we start thinking about down the road, the next CSL renewal proposal, evaluating those models in these same kinds of experiments as we're doing with the dynamical model, is that something we should be thinking about? Because I realize that's sort of we haven't talked about that, it's kind of down the road, but when it comes to machine learning models, down the road is not that far down the road. So that's something I think with all the kinds of experiments that are being done with the dynamical model, we could do those kinds of things with the machine learning models and evaluate both together in a way that would, I think, answer a lot of questions for the community about the usefulness of the machine learning models and what dynamical models and machine learning models can together tell us. So anyway, just an idea. Throw it out there.
I'd ask Kirsten what her answer is.
Yeah, I'd ask Will. Will is much more of a very intense machine learning expert than I am. I'm much more on simple neural networks and interpretability. From my understanding, we're not currently at the state that we can do subseasonal forecasts with the NWP models. They're just unable to get past.
We can't yet, but stuff's moving fast.
It's moving fast. So there's the question of, do we think it'll actually happen? And then, yeah. But I agree, if it happens, we should definitely have ways to evaluate it and compare to our dynamical models. I think that's what the weather community is struggling with right now, is the best way to compare the performance.
Yeah, I guess I just wasn't totally following what kind of experiments could be done with those, right? Like the things Yaga showed are irrelevant for those, it seems, because they don't.
Why would they be irrelevant?
They don't.
They have to be initialized. Couldn't we play with what they're given to start with?
They don't know about the land, right? Aren't they just taking like some basic atmospheric fields, or maybe
For now,
okay.
but people are working with the ocean to incorporate an ocean and the land into the, to extend these out to subseasonal and seasonal timescales. And like I said, it doesn't seem like we're ready for that now, but everything in that field happens so much faster than it does in our field that I think we should be prepared for something like that to happen. And as our system prediction working group and the community that we have, I think we could bring a lot to that kind of evaluation.
Yeah. And are those models, can we just get them and start running them, or are they owned by people?
Yeah, it usually depends who makes it.
Yeah, it depends on who makes it and who's willing, whether they're willing to share it or not. But the one person, Stefan Rasp, that I know is working on the subseasonal timescale at Google, he is somebody, I think there's an openness to working with the community and sharing of that. Obviously not an experimental, they want to be able to demonstrate that it's good before they put it out there, right? But once it's there, I don't think it's hard to grab their data. They do a suite of hindcasts, we can grab their data, do some hindcast comparisons, and then also The models they're putting them out there in GitHub. Now, how easy it is to run, probably somebody at Sizzle can tell us that better than I can.
That sounds interesting.
I mean, I agree. I think that is a very atmosphere-centric sort of priority, right? Because one of the things that is a clear benefit of what we're doing is that we're including, ocean prediction skill. We heard about marine heat waves, right? We didn't hear any biogeochemistry talks today, but usually we do. So, we're really trying to predict the whole Earth system here. And
But they are trying to move in that direction, and we should keep up with what they're doing, I think.
Well, I think, I don't know if it should be under the ESPWG group, but I think what our data sets, be it initialized or not, for the coupled system is one of the few data sets they can actually use to train the ocean or look at state dependent of the ocean. So I think that sort of when they move into this, right, there is so much fewer data in the ocean, they will start training their models on our coupled climate model. It might be the control simulation, not the initialized ones. And I think that will be basically the benchmark is, can you come up with a machine learned model that is as good as CSM? But it will be trained on our data. It's not enough observation. There's no reanalysis for, some
I feel like at the rate this is going, I could see a news announcement in 6 months saying, our model's better than CESM, right? We have a new machine learning model that's better than CESM. Well, if claims are gonna be made like that, we should be prepared to evaluate it rigorously rather than just say, okay, I think.
I mean, and this is a conversation too. I agree that this is like a super important point. I think we're thinking about this a little bit on the SPAT side of things too, right? Could an interface to the predictability community for our process-based models be these kinds of rapidly deployable emulators, right? I mean, and Judith is pointing out, like, certainly people are out there pulling down all of the large ensemble data and coming up with emulators for these things, right? And I mean, on our end, that could be a super powerful tool, right? If we had a skillful emulator for these things, then we could explore the space of initialized predictability potentially in a much more efficient way, right? And try and figure out, and there are a lot of other advantages of these emulators as well, right? Data assimilation becomes almost free, right? Because these emulators are so cheap. So, I mean, I guess in terms of thinking big and for a CSL proposal, do we have any firepower on our end to have people investigate building emulators for some of these predictability timescales?
Yeah, and Kathy's talk, right, there was this questions about reliability and et cetera of the ensemble system and the fact that they're overconfident, right? So there is still some very basic questions of why all models are overconfident and don't have enough spread. But if you think of building an optimal ensemble system with regard to something, these emulators, you can put in spread as one, and I mean, this is what Will would say, right? You can put spread in as one of the metrics that you train your machine learned weather model on. And so once we have those available, we can look at, what do we need to get enough spread in the ocean components, for example. I don't know if the ocean is under dispersed, but I mean the atmosphere is greatly under dispersed. Well, yeah.
I saw a hand pop up.
I'm sorry, Richard.
Okay, Richard.
Hi there. Yeah, I figured out how to speak to this thing again. Yeah, I'm a machine learner and I've been doing it for 30 years. And there's one point that maybe you are raising, but in a different language. One of the nice things about these machine learning methods is you have nice ways of getting a handle on uncertainty with all kinds of nice technical guarantees about valid inference. I don't see yet how you do it with your stuff, and there might be a nice marriage between the two. And I'll leave it at that. That's what I work on, but I'd leave it at that because it's something that together some real progress might be made to get a better handle on uncertainty. And that's the spread problem you mentioned, I think.
Yeah.
So So my own thought is that, you know, we definitely are under dispersed in terms of our ocean initial conditions, which, you know, we never inflate. It's a single condition. We rely on the atmosphere spread. So, you know, we've talked about exploring that. And, you know, I think we have the control data sets to, you know, maybe think about revisiting that, you know, using SMILE. Is there a way that we could introduce some spread in the SMILE FOSSI that we could do it in a sensible way? I mean, do we have, I guess I'm asking you again, do we have a sensible way to introduce spread?
Yeah, I mean,
Redo SMILE for one start.
we talked about this before SMILE. And I mean, I can go back, I think we wrote this up. Like, you know, we can borrow spread from other ocean reanalyses, for instance. You know, one of the issues is that it's not just that the ocean initial conditions are under dispersed or have zero dispersion, but that they have, you know, substantial biases that have very long time scales associated with them, right? And so we would like the spread of the initial conditions also to maybe reflect that. Does that make sense? You know, it's, there's
Like you want the uncertainty to be where the variability of the model is.
Yeah, I mean, you'd like your spread, your range of initial conditions to contain the true initial conditions. But when your initial conditions come from a model that has been run to equilibrium, we know that there are going to be, you know, large scale differences between that state and the true observed state, right? And so how do you get spread that accounts for this model bias? You know, so that might not be resolved if we get spread from an ocean reanalysis and then kind of plunk it into our model. But that would at least be a starting point. But I agree, we can revisit that discussion because I think we had some good directions.
I mean, that sounds like a pretty interesting thing to explore for, you know, a grad student or someone, you know, looking to make a big, you know, a big finding. If you can come back to us and show us that, you know, you get a big improvement in, you know, and so reliability by doing this, like, we would take notice.
So, can I ask a trivial question? So the ocean does not, there's no anomaly initialization in the ocean in SMILE? Like we do for the atmosphere,
No.
to do the ensemble members?
No.
So I mean, that would be a low-hanging fruit to
I
do.
agree. Yeah. But, you know, again, it's the question of, you know, what's your method going to be for introducing appropriate spread? Yeah.
I mean, I think of spread as model error. That's why we have stochastic parameterization and initialization error. The fact that we don't have ocean initializations, I think of them as separately, although I know in the DA setting they become merged. But once we are at CSM, we will have MOM 6. And there's a lot of development going on at GFDL and NYU and M² lines to have machine learned parameterizations in MOM 6. And those will be used, right, to account for high resolution processes, but I mean, that's the same idea as stochastic parameterizations, is you draw different realizations of your subgrid scale state, and so you end up having more spread. And I mean, there are stochastic parameterizations that are being developed for the ocean. It's just something that NCAR, well, if you look at climatologies, people are worried about the added uncertainty. I mean, definitely there's ocean parameterization in the UFS. There's stochastic parameterization for the ocean in the UFS. These are all things that are being developed, yeah. But some of them we'll get for free once we have MOM 6. We just need to switch it on.
Okay. All right, so we will have kind of intrinsic ocean spread in MOM 6, potentially. even enforced configurations. Right?
I think we can use it that way.
And I keep coming back to, if we had our own in-house atmospheric reanalysis that was 80 members, then we would have 80 oceans to use for initializing. And that's probably what we would do.
And there's another, before you get to coupled DA, an ocean-only reanalysis is something that is more readily realizable, right? And that can also give you 80 oceans. And there, the spread will also come from how you might need to inflate these ensemble numbers appropriately to fit. So that kind of could start to address some of these model bias issues. So I guess the point of this is, we might be able to get 80 oceans and 80 atmospheres separately from DA, and that's, a starting point.
All right, we've reached the top of the hour. I'm not seeing any other hands online.
And Google Chrome is ready to be done, so.
All right, well, I want to thank all of our speakers for today. If we could give them another round.
Let's also thank the staff that has helped us.
Yeah, thanks to Paul and his staff. Great work, as usual. And thanks for everyone for participating.
Elizabeth Faircloth has helped us. Elizabeth Faircloth, Teresa, and Kaylin.
Yep.
Yes, thank you.
All right, we'll adjourn. Thanks, everyone.